Hello, welcome back. Today we discuss the concept of block algebra. So we are going to be applying Laplace transforms and transfer functions to a variety of physical systems. These physical systems can be quite complex. They can often be composed of subsystems, or you can also imagine that there is one particular complex system. You think of it in order to simplify and in order to model it, you can think of it as composed of many small subsystems where one input affects a small subsystem, produces some kind of a response which affects another part of the system, and so on. So in order to model these kind of systems and graphically visually show them, we will be using block diagrams, which I described in the last flip lecture. Uh, these block diagrams can become quite complex and can be composed of many different blocks with many different input and output signals coming out from these blocks, which are interconnected with each other. So in order to represent these block diagrams, we have to use different components. In general, a block diagram will be composed of blocks, also referred as functional blocks, summing junctions, and pick-off points. Pick-off points are often called branch points also. Blocks, which is the basic building part of the block diagram, is basically a transfer function where we have some input and some output. So the transfer function is basically describing the output signal divided by the input signal, or the output can also be written as transfer function times the input. So this block can just be opened up as a mathematical equation, which is given by y is equal to g times r. Then we have the summing junctions. Summing junctions can have multiple inward arrows, but only one outward arrow. In this case, we can see that we have three arrows which are coming in, R1, R2, R3. They may or may not have a positive sign. If they do not have a positive sign, we assume that it is getting added up. So in this case, the arrow which is coming out, which is y, is a combination of the three inputs. So R1 gets added up, R2 gets added up, R3 has a negative sign, so it gets subtracted. Finally, the pick-off point. So a pick-off point has one signal which is coming inside. So you may specify it by a dot, by adding a dot at the pick-off point to show that there's a branch over here. So there's one signal which is coming inside, and all the branches which are coming out of the pick-off point have the same signal as the input signal. Now let's see how we can use them for the simplest connection of subsystems. So the simplest way, I can just have multiple subsystems connected is if they basically come one after another. Here we have a cascaded system. So consider a case where an input R is coming to G1, produces an output X2, which goes into G2, produces an output X1, goes into G3, and produces an output Y. So in this case, we can see that X2 is nothing but transfer function times the input R. So G1 times R. X1 is G2 times X2, which itself is equal to G1 times R. So it becomes G2 times G1 times R. Y becomes similarly G3 times G2 times G1 times R. If I wanted to come up with an equivalent representation for this block diagram, I'll just end up having one transfer function where there is one input, the overall input to the system, which is R, the overall output from the system, which is Y, and inside the transfer function is the relationship between Y and R. So you can see that this coefficient of R over here forms the equivalent transfer function that goes inside. So the equivalent transfer function for cascaded system just becomes G3 times G2 times G1. Another configuration can be the parallel block configuration. So over here we have one input R, which is being fed into three transfer functions, three blocks, G1, G2, G3 connected in parallel. They all get come to a summation junction. It is possible that they get added or subtracted based on different scenarios. So if we have added, the corresponding signal gets added in the overall output Y. If the signal has a subtraction, then the corresponding signal gets subtracted in the overall signal. So in this case, the output Y is just an addition of the outputs from each of the blocks, X1, X2, X3. So if I try to see what is the equivalent system of this kind of a parallel block, I just end up getting the summations of G1, G2, G3 corresponding to whatever is going in the summation block. So this ends up being the equivalent transfer function, which is again being found by just the algebraic relationship between Y and R. So whatever is the coefficient of R over here forms the equivalent transfer function. So let's consider the feedback systems. We looked at this in section 1 of the course book also. We looked at several control systems, and we saw that control systems are often composed of measuring an output and feeding it back to an earlier part of the system, and then computing the control action based on them. So let's consider a general block diagram representation where I have R, which is acting as an input. I have an output from the overall system, which is Y. I take a feedback through a transfer function H. This can be done through a sensor, and H can represent the sensor transfer function. I compare the measurement from the input, calculate the difference, and feed it inside the transfer function G, which produces the output Y. This kind of a system, because of the negative associated negative feedback associated, which can be identified by the sign at the summation junction, is referred as the negative feedback closed loop system. When the transfer function on the feedback side H is equal to 1, it is called unity negative feedback system. If instead of negative we had a positive feedback, we can also have a positive feedback if the feedback signal is added up to whatever is the input to the feedback system. The closed loop transfer function in this case can be found by looking at the different mathematical relationships. So the different mathematical relationships can be found by E is equal to R. Let's call this S. So this signal is basically Y times H S. So minus H times Y. So we end up getting the signal E is equal to R minus H times Y. We have the output signal where Y is nothing but transfer function times ES, G times E. So if I substitute for the E from the first equation into the second equation, I end up getting the equation Y is equal to G into R minus HY. Now over here, the input variable is RS and the output variable is YS. If I'm trying to find out the overall transfer function, I should find out whatever is the relationship of the output variable divided by the input variable, which can be done by collecting all the Y terms and the R terms on different side of the equation, and then cross multiplying in order to get the overall transfer function. And this overall transfer function is also referred as the closed loop transfer function of the system. If we have a positive feedback system over here, if we have a positive feedback instead of negative feedback system, you can satisfy yourself by calculating that we will end up having a transfer function y, closed loop transfer function y divided by r is equal to g over 1 minus g times h. So I'll let you do this yourself. So this thing is shown over here that in general, if we have a closed loop, if we have a feedback system where a feedback can be positive or negative, the formula for the equivalent transfer function can be given by g over 1 negative for positive feedback, positive for negative feedback, g times h. In this case, the transfer function, the product g times h is also often referred as the open loop transfer function or the loop gain. So the reason for calling it is that if you go around the loop, but consider that this loop is open, you end up getting a signal which is basically an input times g times h at the end. So this is basically the gain of the system. The open loop gain of the system is basically a product of all the transfer functions that you get while going around the loop. So the next topic is describing different steps, different tricks that you can do in order to simplify a complicated block diagram. So a block diagram can be represented in many permutation and combinations, and you may be trying to find out an equivalent transfer function for the system, or you may just be trying to analyze a small subsystem within a larger block diagram. In order to do these problems, you will have to probably rearrange the block diagram to come up with a few different equivalent systems and analyze it. So some of the steps that you can do are shown over here. So these steps are quite common, and you may consider either understanding how these are done. You may like to memorize what are the common steps that can be done in order to come up with equivalent transfer function. In most cases, you can easily derive them, but if you have difficulty in deriving them on spot, it might be useful to memorize them. So let's say you have two adjacent summation junctions. Then these two adjacent summation junctions can be swapped easily. So you can consider that the signal, let's say you have a signal, let's say you have a signal x1 and you have a signal x2, signal x3, and the output is y. You can see over here that y will be, this signal in the center will be x1 minus x2. So y is going to be equal to x1 minus x2 plus x3. The same relationship can also be found if the two summation junctions were combined together. So if you have x1, x3, x2, you can see that the signal y will remain the same. And if you can combine them, then you can break the summation junction in any order. So you can think of, if this is your summation junction 1, this is your summation junction 2, then this is representing summation junction S2, summation junction S1, and we have X3 which has been brought forward, and X2 is being subtracted afterwards. So you can see that the response out, the overall output y is the same in all cases. The same thing can also be done for the pickoff points. So if you have two pickoff points, then you can arrange them in any order, or you can put them together at one point. Again, all these signals are going to have the same signal x going through them if the input signal is x. If you have a case where you have a pickoff point after the transfer function, then it is possible to bring the pickoff point before the transfer function. So you can see over here that x2 is basically equal to g times x1. So if I wish to keep the same relationship by bringing a pickoff point earlier, then I need to have a transfer function g multiplied over here. So if I'm bringing a pickoff point earlier, then this also has a signal x1. And then in order to get the same signal from the other on the other branch, on the branch which is below, I need to multiply a transfer function on the side of the pickoff point also, on the other side of the pickoff point also. If I'm trying to move the pickoff point after the transfer function, so over here I have the same signal x1 from the pickoff point before. So if I'm moving it after the transfer function, so I'm taking the pickoff point from the signal x2, I need to multiply with the transfer function 1 over g in order to preserve the signal that comes out of it. The same thing can be done for summation junctions. So pickoff points can be moved before or after the branch point. Similarly, summation junctions can also be moved before or after the branch points. So in this case, I have x1 going into the transfer function, then I have a summation junction which is having a signal x2. If I bring the signal earlier, so x3 in this case you can see is going to be equal to g times x1 plus x plus minus x2. So in this case, the signal over here you can see is so if I'm trying to see over here, the signal x3 is based. If I consider this as a signal, let's say y, then x3 is equal to g times y. Now y is a combination of x1 plus whatever is this signal over here. Let's call it signal r plus minus y plus y is x1 plus minus r. So in order to get the same relationship from x3, I need to have a 1 over g transfer function which is multiplied from the x2. You can do the same thing to see over here that if I move the summation junction, if I have a summation junction before a transfer function and I wish to move it afterwards, then I need to multiply a transfer function on the other side of the summation junction over here also. So to summarize, I've shown to you that summation junctions and pickoff points can be swapped. Transfer function and pickoff points can be swapped with some modifications. Similarly, the summation junction and transfer function can also be brought back and forth based on some modifications on the branches. What is generally avoided is that if you have a what we usually try to avoid is trying to move the summation junctions before or after the pickoff point. So if you have a case where a summation junction is before is next to a pickoff point, then it is generally not advised to try and swap these ones because the mathematics corresponding to it is quite difficult to do. Let us look at the example now. So in this case, consider a feedback system. Let's consider that the transfer functions on the forward loop side are G1 and G2, and let's consider that the feedback side, the transfer function is H. So in this case, we can see that The forward loop side we can just simplify as R summation junction G1 G2 gives us the output YS, which is taken on the feedback, and we have a transfer function H on the feedback side. So this is a negative feedback. So we have seen that the closed loop transfer function, the closed loop transfer function for feedback system is Ts given by G, which is the forward loop transfer function. So G1 times, sorry, we assume that the forward loop transfer function, this one is given by G. So the closed loop transfer function is given by Ts is equal to forward loop transfer function, which is G over 1 plus GH. So this ends up being G1 G2 over 1 plus G1 G2 H, which ends up being, which can be simplified as 2 over S plus 1 times 3S S minus 2 1 plus 2 over S plus 1 3S S minus 2 times 3, which gives us so if we multiply this, we end up getting 6S S plus 1 into S minus 2 over S plus 1 S minus S minus 2 plus 18S over S plus 1 into S minus 2. So the denominator from both numerator and denominator can be cancelled out. So it sounds a little roundabout that each of the numerator and denominator itself is a fraction with a denominator which is common. And this can be simplified as 6S S squared plus 17S minus 2. Let us look at a few more examples of block diagram equivalence. These block diagram equivalence examples are going to be using the rules that I explained to you in the previous page of the course book. So we'll get some practice on how to apply them. We'll see a lot of these examples is about recognizing patterns of block diagrams, simplifying a small portion, and then continuing to do it with the other portions of the block diagram. A little bit of practice with this will soon make you experts in how to solve these kind of problems. So let's look at the first example. So over here, we can see that we have a block diagram which has a few loops, 2 loops. So there is a signal which is going in, and then you can think of this as having an outer loop and having an inner loop. So this is not exactly a feedback loop because both the signals are going in the same direction. So if you are trying to simplify this kind of a block diagram, it may be worthwhile to think about where to start the problem from. So we could try to think about, if we try to think about how to simplify the outer loop, then it depends on a lot of functions with a lot of blocks and signals in the inner loop, and it will be difficult to simplify it in the beginning. So it is logical to try and start somewhere, choose an inner loop and try to simplify that in the beginning. So if we look at this inner loop, we can see that we have a signal. There is a signal which is going into G4 and G3 and then going to summation junction and getting added together. So this is just like having two parallel blocks, and the two parallel blocks, because there's no sign over here, so they are both assumed positive to the summation junction, can just be added together. Now we can see that this portion of the block diagram is just the feedback system. We know the formula for this. The formula for this is given by closed loop transfer function is times whatever is the transfer function on the forward side, 1 plus or minus. So in this case, it is a negative feedback over here. So we have a plus open loop transfer function, which is G times H. In this case, we have a unity feedback, so H is just equal to 1. So G over here is nothing but G2 times G3 plus G4. So if we do that, so if we look at that, so G2 times G3 plus G4, we can simplify that into this form, and now we can multiply the two cascaded systems and find out the overall transfer function as over here. So this one is the equivalent transfer function, which is describing the relationship between the output Laplace variable divided by the input Laplace variable. So this is the equivalent transfer function. The next problem is asking about the transfer function x0 divided by d. In this case, we can see that we have a block diagram with two inputs, xi and d. So we have to find out a transfer function which is only for one particular input. In this case, whichever input is not being considered, whichever input is not being used, we can assume that that input is equal to 0. So we can assume that there's a transfer function 0. So this basically results in a 0 signal over here. So whatever is this signal just goes over here, but then you have a negative sign. So this signal, so if you think about the signal over here, let's say E, this is xi, and this is, let's say, x2, then E will just be equal to xi minus x2, where xi is 0, so just equal to negative x2. So we can consider that this summation junction is just acting like a transfer function with -1. So we can rearrange the block diagram. So we can consider that D is coming into the summation junction, goes through cascaded blocks, 1 over s plus 1 multiplied with 1 over s plus 1. So gives us a square, 1 over s plus 1 square. This gives us the output variable, which is xo. Xo comes back into 1 over s plus 1. It goes into the summation junction. One of the signal is 0. The other one is, so the output, as I described over here, that this summation junction with 1 0 input, and they just inverts the signal based on whatever the description I described to you over here. So this portion can just be replaced with a transfer function -1. So I can also multiply the three blocks in the feedback side. They are 1 over s plus 1, my -1k. So I end up getting on the feedback side, my equivalent transfer function is -k over s plus 1. So now the overall transfer function is, we can see a positive feedback system. So I have the forward loop transfer function, which is 1 over s plus 1 squared, 1 negative because of the positive feedback. And then I have just the product of the forward loop transfer function G and the feedback side transfer function h. So I end up getting negative k into s plus 1 cube. So if I simplify this, I end up getting this as the final result. Example 3. So over here, we can see that we have two summation junctions. And in the first summation junction, we have both G2 and G3. One is coming from above, one is coming from below. So don't be fooled by these going from different directions. But if you see, we can write down all these, we can combine some, first of all, the summation junctions into a single one. We can think of all the summation junctions lumped into one. So G1 is giving X naught. Then from X naught signal, we have G2. We have G3. And we have G4. All these, so G2 is getting negated. G3 is getting also negated. G4 is having a positive feedback. So if I'm looking at the feedback side, I have basically G2, G3, G4, which are connected in parallel. So if I combine these, I can add up all the parallel blocks. G4 was not getting negated, it was having a positive feedback, but G2 and G3 were both getting negated. So I end up having on the feedback side, G4 minus G2 minus G3, and then I have a positive feedback. So in order to find out the closed loop transfer function, I can consider this as transfer function G, this as transfer function H, and applying the formula for closed loop transfer function with positive feedback, I end up getting this solution. Let us look at example 4. In example 4, it is I have a few loops and they are all interconnected. So I have a loop which is, I have a feedback loop which is lower, and I have an upper feedback loop. And in this case, you can see further that I don't really have a concept of inner or outer loop. So in the beginning, I described that you can start somewhere from an inner loop, simplify it, and then simplify an outer loop. It will not work. There are actually multiple ways of doing this problem. What I'm going to do is, so you can choose different pick-off point or summation junctions and then move the direction. What I'm going to do is I'll choose this pick-off point and move it behind G3. Alternatively, you could also use this summation junction and move it in front of G1 and try to do the problem. One of the things that you may consider is, should you move a pick-off point before G2? In which case, the next one will have a summation junction and the pick-off point next to each other, and they will be very difficult to swap. So I suggest not trying to pull the summation junction behind. So do not do this, or do not move the pick-off point ahead. These two things will make the problem much more difficult. But other than that, the ways that you may consider approaching this problem, the different ways, and you can find another way. These are not the only necessary ways. The different ways that you can try approaching this problem is either move the pick-off point behind or move the summation junction in front of G1. So you can choose one of these possible ways in order to approach this problem. Okay, so let's try to take the approach of moving the pick-off point behind G3. If we try to move the pickoff point behind G3, so over here, we'll end up having a G3 on the getting divided on the feedback side. So if I move it behind G3, if I move it behind G3, then I do not have this signal, but instead I have this signal. But in order to preserve the same signal that is going into G5, I need to divide by 1 over G3. So I end up getting, on the feedback side, I end up getting G5 divided by G3. Now, I can combine my G2 and G3 on the cascaded blocks. They do not have any signal in bit. They do not have any summation junction or pickoff point between. And this loop ends up being inside this outer loop. So I can simplify the inner loop and get a solution also. So that's one possible way. But over here, I've gone another step further. I am now moving the summation junction in front of G1. So if I move the summation junction in front of G1, again, I'll have to divide 1 by G1 on the summation sides in order to get the same signal out of G1, in order to get the same signal going into G2 times G3. So if I do if I multiply if I do this, then I end up having this loop, this feedback signal, and this feedback signal end up being parallel to each other. So I can add up these two, and now I can apply. Now I can consider that this one is the transfer function G, this one is the transfer function H, and I can apply the formula for the closed loop transfer function with negative feedback, and I end up getting the overall equivalent transfer function as this one. So as I said, there are multiple ways of doing this. So you can also try simplifying the inner loop and applying the similar transfer function. You can see that if I consider this as G and this as H, I can find out the inner loop has a transfer function G2 G3 over 1 plus G2 G3 G4. And then you can see that you can multiply it with G1 on the forward side and then apply the same formula of closed loop transfer function again and verify it yourself that you end up getting the same answer as over here. Let's look at example 5. In example 5, we have a feedback loop, but then there are several other loops which are inside it. So we can see that there is we have two parallel signals over here. So here we have 3 over S, and there is no signal over here. So whatever is the signal, let's say X2 goes over here, X2. So this can just be considered as a transfer function of 1. So if I combine these two, if I consider them in parallel, I end up having 3 over S. So I can find out the equivalent transfer function over here by 3 over S plus 1, which ends up giving me 3 plus S over S as this block. Similarly, so now on the forward side, I end up having two cascaded blocks. I can multiply these two cascaded blocks and get just one transfer function by the product of 3 plus S over S and 6S over S plus 2. On the feedback side, I can consider that I have a feedback loop over here with a positive feedback. So applying the closed loop transfer function, I end up getting a form. I can apply the formula for the closed loop transfer function. So this is G, and I have a unity feedback. So I end up having G over 1 minus G for positive feedback. So I end up getting S over 1 minus S. Now I can multiply these two cascaded blocks to get 2s over 1 minus s squared. And finally, I can find out the overall transfer function, the equivalent transfer function for the entire block diagram by applying the formula again. I can consider this as g and this as h. So my closed-loop transfer function is g over 1 plus gh. So if I substitute for g and h and simplify, I end up getting this as the final result. So I will stop the flipped lecture over here. There's one more example 6. This one is a relatively difficult example to do. This is more put as a challenge problem for you. So I encourage you to try doing this without looking at the solution and then see how the solution is done. But this is above the level of difficulty that I'll be putting on the test and the examinations for this particular course. So you will see that it uses a different approach rather than trying to simplify different parts of the block diagram. It first tries to open up the block diagram and then simplify them. So this is different from the previous problems that we did, where every time we tried to look at a few sections and then simplify them before moving on to the next one. So I'll end the flipped lecture over here. Thank you for your attention.